Morning. So let's start the chapter 8 today. Last class we lost so much time with that survey, more than half of the class. So we have to finish this chapter within 2 classes, right? The good thing is that you know most of the things in this chapter. As we go forward, you will see that there are a lot of things which are just revision and things which you learn in lab, especially Lewis structures, drawing Lewis structures. You know this already, so this will go easy. So the topics we are going to cover in this chapter are types of bonds and ionic bonding and covalent bonding. Yes? For the final. I'll bring it next week. So ionic bonding and covalent bonding, those are the 2 types of bonds. Then we will look into shapes of molecules. That is where we learn the Lewis structure, and remember those shapes and all? So those things, we will look at them one more time. So there are 2 different types of bonds in chemical compounds. Well, first of all, what do we mean by a bond? Bonding. Bonding means just like, it's the word we use in our day-to-day life. Same things. 2 things bonded together means a force which is holding something together, right? So that's the same thing. So chemical bond is the force which holds atoms together in a molecule or a compound. That is the only difference. Meaning is the same. A force which is holding things together. That's what a bond means. So there are 2 types of chemical bonds, ionic bonds and covalent bonds. These are the 2 types of chemical bonds. Now here is a picture of 2 compounds. First one is calcium carbonate. Is that an ionic compound? What are ionic compounds? Something which has a metal ion in it, right? So that is an ionic compound, and there is something else below, carbon dioxide. What type of compound is that? Well, what is the name we learned in chapter 2 for such compounds? Molecular compounds, right? We learned ionic compounds and molecular compounds. Ionic compounds which have metal ions in it. Molecular compounds in which there are no metal ions, 2 or more non-metals together, correct? We are going to connect those 2 words to these bonds also. In ionic compounds, ions are held together by ionic bonds. So all ionic compounds have ionic bond. And what are ionic bond? Once again, the electrostatic forces or forces between oppositely charged ions. Ionic compound between metal and non-metal means usually metals are positively charged, non-metals are negatively charged, and the positive and negative charge attract each other. That is how the compounds will form, right? So that force of attraction between the positive and negative charges, that is what is called an ionic bond. So ionic bonds present in ionic compounds. So the other types of compounds we know, molecular compounds in which there are no metal ions present. The bond present is called covalent bond. So molecular compounds have covalent bonds, and therefore we call sometimes molecular compounds covalent compounds also. Okay? So what do we mean by covalent? Covalent compound means electrons are not transferred, but electrons are shared. Like in Lewis structure when we talked about 2 atoms sharing electrons, that type of bonds are covalent bonds where they are sharing electrons. Okay? So these are the 2 bonds, ionic compounds with ionic bonds and molecular compounds with covalent bonds. Now this table we have seen in chapter 2 also, general properties of ionic and covalent substances. As I said, covalent substance and molecular substance, they are one and the same. It's just two ways of naming them. So we know that ionic compounds are usually crystalline solids, and they are hard and brittle. They have high melting and boiling point, and they are good electrical conductors when they are molten or in solution, and usually they are soluble in water, but not in carbon tetrachloride. Carbon tetrachloride, CCl4, which is a molecular compound, right? So ionic compounds are usually soluble in water, not in other molecular solvents. Whereas covalent compounds or molecular compounds, they are usually gases, liquids, or rarely solids, and they are brittle and weak solids, or they are soft and waxy. Then they have low melting and boiling point, poor conductors of electricity and heat, and they are often more soluble in carbon tetrachloride but not in water. So if you compare the properties of ionic compounds and molecular compounds, they are opposite properties, right? If something has high, then the other thing has low. So it's this is a table. This is what I said. This you have seen in chapter 2, this table, the same table, under the name General Properties of Ionic and Molecular Substances. Here we just have changed the name to covalent substances because we are learning that new word. That is the only difference. Now we will look into a little more detail on ionic bonds. So ionic bond, we know that ionic bond is created by electrostatic forces of attraction between oppositely charged ions. Positive and negative ions attract each other. That force of attraction is called electrostatic force of attraction, and that is what is causing the ionic bond. Now, of course, if it's an ionic compound, it happens between a metal and non-metal. And what actually happens when they attract each other? Electrons are transferred between the positively charged ion and negatively charged ion. Let's take an example. Sodium chloride, an ionic compound. We say that for sodium chloride, we have Na plus ion and Cl minus ion, and these two come together and form NaCl, the compound, right? Let's think about what is going on in each of them. When we say Na plus, sodium is atomic number 11. Neutral sodium has 11 protons and 11 electrons. Na plus has how many electrons? 10. 1 electron less, right? What happened to that 1 electron? Is there a pool somewhere outside in the space where all these electrons go and stay together? No, oh no, we are not going to put them in the socks either. So, what happened to that electron which sodium lost? That electron has been transferred to a neutral chlorine. That is when chlorine becomes Cl minus. Cl minus means one extra electron, right? Same thing, where do the extra electrons come from? Again, we don't have a common source where whenever somebody feels like becoming negative, oh, go and take some electrons from there. We don't have any pool like that for storing electrons or taking electrons. No electron banks available. So what actually happens is, sodium, the same time when sodium loses this electron is actually transferred to chlorine. That is when chlorine becomes Cl minus. And once they become positive and negative, they'll start attracting each other. And they come together and form an ionic bond between them, and then we have the neutral sodium chloride. That's what happens with every positive ion and negative ion. That is why when we make when we write the formulas, they have to be electrically neutral. The number of positive charges and number of negative charges has to be the same, because number of positive charges means that many electrons are lost from the metals, and the same number of electrons has to be gained by the non-metal. That is why the charges has to be the same. Okay? So what happens in ionic bond? Electrons are transferred from the positive ion to the negative ion. Now these are extremely strong bonds. Ionic compounds or ionic bonds compared to covalent bonds, they are extremely strong. Now covalent bonds, a bond usually created by sharing of electron. There is no transfer of electrons in covalent bonds. Okay, that is the main difference between ionic bond and a covalent bond. Ionic bond, there is transfer of electrons. Covalent bond, there is no transfer of electron. It occurs by sharing of electrons. And covalent bonds happens between two nonmetals. So they share electrons. So there is no charge arising. So of course it is neutral. And as I said, electrons are not transferred. They are shared. And electrons usually are shared also in pairs. Remember when we talked about Lewis structures, I said electrons usually exist as pairs, right? When they are shared, so that's what it says. Electrons are typically shared in pairs, and compared to ionic bonds, these are weaker bonds. Ionic bonds are stronger than covalent bonds. So here are some compounds. Let's try to identify the type of bonding in each of them. NaF, what type of bond? Ionic bond. It is an ionic compound, therefore it should have ionic bond. How about ClO2? Covalent bond. How about FeSO4? Only ionic bond? Ionic and covalent. Between iron and sulfur or oxygen, there could be ionic bond because it is a metal and non-metal. How about sulfur and oxygens? SO4. Both are non-metals, right? Well, we talked about SO4 2 minus, sulfate ion. Sulfate ion, how that sulfur and 4 oxygens will stay together? Covalent bonds between sulfur and oxygen, right? So this particular compound has ionic and covalent bond. Do not think that one compound can have only one type of bond. Okay? Based on what is the conductivity, they can have ionic and covalent bonds, or ionic only or covalent only. Okay? So all you are going to look for is whether there is a metal present. If metal present, definitely there will be ionic bond. And if there are more than one non-metal, then there will be covalent bond also present. How about the fourth one, SO2? Only covalent bond, only non-metals, right? How about the last one? Ionic only or ionic and covalent, right? There is calcium present, so there should be definitely ionic bond. But look at that polyatomic ion. You have more than one non-metal present there, right? So that polyatomic ion between chlorine and oxygen, which is both are non-metal, therefore there should be some covalent bond also present. So yes, that is our answer. NaF only ionic bonding, ClO2 only covalent, then FeSO4 ionic and covalent, SO2 covalent only, and CaClO2 twice ionic and covalent bond. Now, familiar? Polar, non-polar? We have seen those words in the lab, right? So, covalent bonds could be two general types, polar covalent or non-polar covalent. Now, what do we mean by polar covalent? Polar bonds are covalent bonds created by unequal sharing between or unequal sharing of electrons. Okay, we will explain that a little more in detail, but polar means there is unequal sharing of electrons. Remember when we were indicating polarity, we put an arrow towards the more electronegative atom because we said this more electronegative atom is attracting those electrons more closer to itself, right? That means there is no equal sharing. Equal sharing means they should keep right in the middle and both of them should share, right? But there is no equal sharing. That is when you have polar bonds. Whereas Non-polar bonds means equal sharing. There is no fight between the two atoms. It's kept right in the middle. Now, how do we get this unequal sharing? What causes this unequal sharing? This occurs when different elements are covalently bonded to one another. And why different element? Because different elements have different electronegativity. Whereas non-polar covalent bonds occurs when all the elements in the molecule are the same, or all elements in the molecule have the same electronegativity. Electronegativity is the culprit which creates this problem there, equal sharing or unequal sharing. As long as, see, non-polar covalent, it's easy to understand. If it's between two oxygens, both oxygens have same electronegativity. So nobody can say I am stronger than the other, right? So there is no unequal sharing. Now another case is both elements, it's two different elements, like let's say phosphorus and hydrogen. They both have, if you look at the electronegativities, they both have exactly the same electronegativity. Even though they are two different elements, phosphorus and hydrogen, if they are having same electronegativity, the force, it's the same, right? So they cannot say, you know, somebody can hold the electrons closer to itself. So as long as it's the same element or elements with same electronegativity, there is no unequal sharing, therefore no polar bonds. In other cases, you will get polar bonds. So, before we go to electronegativity, let's just summarize the classification of bonding. So we said chemical bonds, the force which hold atoms or elements together in a molecule. There are two types of bonds, ionic and covalent. First, ionic bond, there is transfer of electrons, like as I showed you in NaCl. There is transfer of electron and there is no sharing business. Electron is transferred from the positive ion to the negative ion. They are not sharing it in between. Yes? Before it share what? Yeah. No. When they start the transfer, they are not sharing at all. Okay? Sodium is staying as sodium, chlorine is staying as chlorine. When the electron transfer from sodium to chlorine, that is when they become positive and negative. And then they attract each other. There is no sharing business whatsoever. That's okay. As long as you get the picture clear, that's fine. So there is no sharing of electrons at all in ionic bonds. Whereas covalent bonds, we have two different types, polar and non-polar. Well, non-polar, again there is no transfer in any of the covalent bonds, and in non-polar especially, there is equal sharing of electrons. Right in the middle, both of them on sit equally. Whereas polar is somewhere, you know, shaky. That is, it doesn't share equally, and the greater the electronegativity difference, more polar it becomes. We are going to see that in the next slide. So, the polar covalent bonds, electrons are again not shared equally. This results in the unequal sharing, which can be described as a partial electron transfer. So in ionic bonds, remember, we said there is complete electron transfer, right? But in polar covalent bonds, they are not completely transferring it, but we can call it partial because someone is holding those electrons more closer to itself than the other. So here is a picture of hydrogen fluoride, fluorine and hydrogen, both are non-metals. So there is a covalent bond, they are sharing a pair of electrons between them, but that sharing is not equal. Okay? So because the sharing is not equal, this results partial charges on the elements. So that partial charge is being represented on the top as delta minus and delta positive. What do we mean by those delta minus and delta positive? So you have, let's imagine, you have two atoms, hydrogen and fluorine, and there are two electrons sitting right in the middle. whoever is holding the electrons closer to itself, that has a higher negative charge around it, because electrons are negatively charged, right? So whoever is holding the negative charge closer to itself, that particular element attains a partial negative charge, a higher negative charge. That's what is shown as that delta negative. So the other element, from hydrogen, the electrons are so far away. That means in hydrogen we will say there is a lack of negative charge. Lack of negative charge can be represented as higher positive charge, because they are opposites of each other, right? That is why we put a partial positive charge on hydrogen. Now, you don't have to think in this way. When you look at electronegativity, this becomes more clear. So electronegativity, again, the definition of electronegativity is the ability of an atom to attract a bonding pair of electrons, okay, who can keep the electrons more closer to itself. So this electronegativity was proposed by the scientist Linus Pauling in 1930s, and a difference in electronegativity between the atoms in a covalent bond results in a polar covalent bond. So why we get polar covalent bond? There is unequal sharing. Why they share unequally? Because they have a different electronegativity. Electronegativity is the ability of an element to attract the bonding pair to itself. So the higher electronegative atom will attract the electrons closer to itself. Higher electronegative means you can think of this as strength. Whoever is more stronger, they get the electrons closer to themselves. So the higher electronegative element attract the electrons closer to itself, and therefore getting what charge? A partial negative charge. So to decide who has the partial negative charge and who has the partial positive charge, all you need is to look at their electronegativities. The one has the higher electronegativity get the partial negative charge, electronegativity. So it becomes negative, and the other one is partially positive. That is how we represent the partial positive and partial negative charge. So as it says, the greater the difference in electronegativity, the more polar that bond joins the atoms. Now, if there is no difference in electronegativity between atoms, then you don't have a polar bond. It is a non-polar bond. So electronegativity tells us which element has the greater pull on electrons, and the more electronegative element get the partial negative charge, and the less electronegative element loses the electron density around it, therefore getting a partial positive charge. So if you look at the electronegativities of fluorine and hydrogen, you will see that fluorine has higher electronegativity. Actually, fluorine is the most electronegative element on the periodic table. So fluorine gets a higher pull on electrons, a greater hold on those two electrons. So fluorine is partially negative, whereas hydrogen, because its electronegativity is less, it has a less pull on electron, therefore it is partially positive. So here is the table from your book again, figure 8.5, which shows the main group elements and most of the transition elements with their electronegativities. As you can see, you see the more electronegative elements in the right hand top corner of the periodic table. Fluorine 4, then comes oxygen 3.4, nitrogen, chlorine 3.2, nitrogen 3. As you can see, all those numbers are high, right? Whereas you look at the left side, lower side of the periodic table, you find the least electronegative elements in the left side, lower side of the periodic table. Look at francium, cesium, radium and all. So less. Yes?
So metals
That is why metals usually tend to lose electrons. They won't hold electrons. That's why they don't form negative ions. So electronegativity is the power of holding electrons, right? Metals do not usually hold electrons. They usually just get rid of them and becomes positive. That is why their electronegativity is very less. Whereas non-metals like fluorine, chlorine, oxygen, we never see them becoming positive. They are always negatively charged. Why? Because they have higher electronegativity. So they would like to hold on to the electrons or gain more electrons if possible. Because the electronegativity is not being calculated for them. Not on this particular one. Usually we work around with these are the compounds which normally forms, these are the elements which normally form compounds, so we need to know their electronegativities. Whereas the rest of them, like most of the elements in the inner transition series, those two periods you see on the bottom, they exist mostly in lab. So you are not going to worry about their electronegativities. Okay? At least let us put it this way. For the scope of this class, you don't need to know about the electronegativities of those bottom ones. Okay? Because you won't be seeing any compounds formed by those atoms. You will be mostly focusing on main group. Okay? Only the main group elements. So, if you can put a trend on electronegativity, this is the trend. You have seen the numbers. And you can see the color intensity also. The right side, topmost, more electronegative elements. Left side, bottom, less electronegative elements. So if you put a trend in a group, from bottom if you go, it's increasing. In a period, from left to right, it is increasing. So you can, if you want to think of this as decreasing, then you can, you can turn the arrows the other way. That's all. So if you put a diagonal arrow, how would that go? Like this. Right? Okay, that's for the increasing, guys. My arrow is for increasing, not for the decreasing. Okay. So, one more time, the difference in electronegativity between metals and non-metals is so large that electrons are transferred, not shared. That answers Jason's question. Yeah. Because it's, okay, let's think of this way. Sodium and chlorine. Sodium has electronegativity of 1.1. Chlorine has 3.2, 3 times, right? So when they come together, chlorine is so much powerful than sodium that it's not just sharing that pair of electrons. Chlorine is like, I'm going to take one electron from you because I'm so strong. So it pulls away that electron. And sodium is so weak that it has no way, it will just give up the electron. That is why the electrons get transferred. But between, let's say, the hydrogen and fluorine, we have seen fluorine is 4, hydrogen is 2 point something. So it's not, almost they are like half. Okay? So hydrogen is not going to give away its electron. It will say, we will still share. Well, you can keep it more closer to yourself, but we will still share. That's what.
Why don't they just take the electron and run? Why are they together now? If one of them just takes it.
Okay, why they don't run, right? Well, once somebody take it, something else comes into the picture. That person becomes negative, the other person becomes positive. Law of nature, positive and negative has to attract each other, then they don't have any control over it. Electron becomes negative, yes, exactly. Then the electrostatic forces of attraction, that cannot be changed. If there is something positive and negative, it doesn't matter who was strong or weak, those two forces will attract.
Is the process of taking the electron then bonding?
Well, these things happen so fast that you cannot kind of think of that as a day-to-day activity, like somebody losing electron, someone taking it, becoming positive, becoming negative, then they attract. You know, these things happen simultaneously so fast. We are trying to kind of break it down, try to visualize in a step-by-step process, but you just cannot pinpoint what happens first, or things like that. It's beyond our imagination power. It happens so fast.
So that means we are achieving for the neutrality of both. And if they attract each other regardless of it means they have to be neutral.
Yes, that is the goal. When there is positive and negative stuff, they attract each other to become neutral. Okay, charge becomes neutral, but the electrons still stay with the chlorine. Sodium do not have an electron, but the charges, that is a different force of attraction. Yes. They are just sharing, they are just keeping in between, and they are staying as themselves. They are saying that, okay, it's me, it's you, we have a pair in between and we'll just keep it there. Because they want to attain octet. So as long as, they have 8 around them, they are happy, they don't care. Okay? So, the greater the electronegativity difference, the more polar the bond is. Let's look at the compounds given there, and of course, if you look at the electronegativity differences, silicon and fluorine, greater the electronegativity, let's look at all 4 compounds, one is fluorine, right? So all you have to do is compare the electronegativity of the other element. Well, here it is between fluorine. Is there any polarity? There is no polarity because both fluorines are equally strong, right? So they are not pulling each other or anything. They are just keeping in the middle, sharing, so that they can have 8 around it. That's all. But when it comes to oxygen and fluorine, who keeps the electrons closer to itself? Fluorine. Therefore, who is partially negative? Whoever keeps it to themselves, they become partially negative, right? Remember, electrons are negatively charged. So whoever keeps it closer to themselves, that guy is negative. So fluorine is negative, oxygen is positive. How about nitrogen fluorine? Fluorine, well, I said fluorine is the most electronegative element. So in everything, if fluorine is present, fluorine is going to be the partially negative element. The other one will be partially positive. If you break the bond, yeah, equally in the sense, if it was sodium and chloride, if you break the bond, then that one electron which chlorine gained can go back to sodium. So, which of the following molecules have polar bonds? If a bond is polar, which atom has a partial negative charge? That's the activity. Sulfur dioxide, you use the electronegativity table from your book. Keep that figure open. Sulfur dioxide, is it polar bond or not? It is polar. Okay. Who will have the partial negative charge? Oxygen, right? Because oxygen has more electronegativity than sulfur. Okay. How about N2? Yes, Jason. Well, if you remember the structure of sulfur dioxide, sulfur was in the middle, oxygens were on each side. So, sulfur and oxygen, between sulfur and oxygen there are bonds, right? So, you are looking at the bond, only the bond. Yeah. How about N2? Non-polar, because it's 2 nitrogens. There is no difference at all. pH3. Look at the electronegativities. You have the table with you. Phosphorus and hydrogen. Exactly same electronegativity. Therefore, nobody can say I'm going to pull it more to myself, right? Okay, how about CCl4? We are just looking at the bond. Remember, the molecule can be polar. That comes from a different thing. Okay, we are just looking at the bond, polar bond or not. Okay, how about CCl4? Polar bonds. Okay, how about O3? Non-polar bond, 3 oxygens, right? Okay, let's look at the answers. Yes. Oh, we didn't do the partial. Well, you know what do you mean by partial negative charges, right? Whichever is more electronegative, you have the partial negative charge on that one. Okay, let's do a clicker question. Everyone ready? Very easy question. Read carefully and choose the correct answer. Everybody has clickers today? You need only a minute, guys. Not even that, but I'm asking for non-polar, okay? Which one? Oxygen. I want 100%. Yes. So, we were talking about covalent bonding so far, polar, non-polar covalent bonds. Let's briefly look into little bit details of ionic bonding also. Now, this thing, we know this already, all these sentences, but let's just read and remember one more time. Each element immediately following a noble gas is a metal. Well, on the periodic table, we know that. And metals lose electrons forming positive charge to become cations. We know that also. Now, each element immediately preceding a noble gas is a non-metal. Yeah, usually group 7, that is what immediately preceding the noble gas. And non-metals usually gain electrons forming negatively charged anions. Now, formation of these cations and anions or formation of ions itself, it relates to electronic configuration of the element. Okay? We learned electronic configuration in last chapter, and if you carefully look into the electronic configuration of the ion, you will see that the ions either gain electrons or lose electrons in order to have the same electronic configuration as its nearby noble gas. That's what we call them, noble gas. Everyone wants to be like them. They cannot be, they are all different. But at least they will think in the number of electrons, let me be like them. So, for metals, it's easy for them to lose electron and become like the preceding noble gas, like sodium. Sodium is number 11. It's easy for sodium to lose 1 electron and be like 10 electrons, Na+, just like neon who has 10 electrons. Next one, magnesium, number 12. Group 2 always form 2+ ions. Magnesium loses 2 electrons For magnesium, it's easy to lose 2 electrons and become like neon rather than gaining 1, 2, 3, 4, 5, 6 more electrons and become like argon. Make sense? If you look at the periodic table, they are just going to look for who is nearby. Okay? So group 1, 2 and 3, for them it's easy for them to lose that 1, 2 or 3 electrons and become like the noble gas just before them. Group 4, right in the middle, they can either gain 4 electrons or lose 4 electrons. That's why we are not talking about group 4 when we talk about the ions. Whereas from group 5 for nitrogen, it's easy to gain 3 electrons rather than losing 5 electrons. Okay? So whatever they are doing, that is all for this one purpose, to be isoelectronic with a noble gas. What do we mean by isoelectronic? Have the same electronic configuration. That's what they do. Now, in ionic compounds, so we know that sodium becomes Na plus because it is easy for sodium to lose that electron and become neon, and for chlorine just wants one more electron to become like argon, so it gains that electron and becomes Cl minus. And when in ions, same charge will repel each other. We know that, right? Electric field and magnetic field, they follow the same rule. Same charge will repel each other, opposite charges will attract each other. Same like in magnetic field, same poles will repel each other, opposite poles attract each other. So in ions, the like charges will repel each other and opposite charges will attract each other. So you can imagine, it's in one positive charge and one negative charge, it's easy for us to visualize. But when so many of them are together in an ionic compound, as you can see in this picture, what they are trying to show. Let's say this is sodium chloride. The green is sodium, and let's say this is chloride ions. Sodium and sodium, they are positively charged, right? So they try to repel each other. Chlorine and chlorine, they are both negatively charged. They try to repel each other, but sodium and chlorine, they try to attract each other. So when this thing goes on, in so many millions of, between so many millions of ions, there is a 3-dimensional regular pattern forms. And that 3-dimensional regular pattern, the geometrical pattern is called crystal lattice. Okay? So that 3-dimensional pattern's name is crystal lattice. And different ionic compounds have different crystal lattice because their charges might be different and sizes might be different. There are two things come into the picture, the charge and the size. So once again, crystal lattice means the pattern obtained when an ion, represented as a charged sphere in the picture, exerts a force equally on all directions. As I said, there are a lot of things going on there. Like charges repelling each other, opposite charges attracting each other. And there are two different types of like charges, negative ions and positive ions. So all those things come together, you get the crystal lattice. Now, of course, cations and anions must come into contact for a crystal lattice to form. So this is the picture of sodium chloride, NaCl crystal. When we look at sodium chloride, table salt, we see like crystals like this, right? And if you look really through a microscope, you will see that each of those crystals are really in the same pattern. And that pattern is this. Don't think of this as bonds, it's just showing you the 3-dimensional picture of, let's say if you take a crystal, one single crystal of sodium chloride, and look through a powerful microscope, how do you see how the atoms are arranged? Okay? They are arranged in such a way that oppositely charged ions are together, whereas same charges are away from each other. That is how they get arranged. You do not have to worry about how to arrange them, okay? Nature will do that. Now, when we talk about properties of ionic solids, we said ionic compounds are usually crystalline solids, right? And they are hard and brittle, and they do not conduct electricity when in the solid state. They conduct electricity only when they are in solution or they are molten. You can think of this way. Let's say this is a big chunk of sodium chloride, and if you keep a sharp blade and if you hammer it, you will see that they cut also in a pattern, right? The crystals cut and come across in a pattern. That's what it's showing. Let's say this is the big chunk, and let's say this is where you exert that blade here and put the force. What happens is they cut in that pattern so that again another smaller crystal lattice is formed. Okay? Maybe the next picture. Yeah. So the ions are arranged in that regular geometric pattern, which maximizes the attractive forces between opposite charges and minimizes the repulsive forces between the same charges. So if you shatter forcefully, like if you struck forcefully, it can shatter in that pattern. And when in the solid state, because of these forces which are holding them in its place, the ions are not moving around, right? If the ions are not moving around, it cannot conduct electricity. Remember when we learned about electrolytes and non-electrolytes? In solution, when you have positive and negative ions moving around, they can complete the circuit, and that's when we say that is an electrolyte, something which can conduct electricity. But solid sodium chloride, ions are not moving around, they are forcefully kept in that lattice. If they are fixed in a position, how can they move around and complete the circuit? They cannot. Therefore, they are very poor conductors of electricity in the solid state.
So they're all attracted to each other, so it's keeping them connected. When you break off this package, you just put it right back together.
Well, it's the force you supplied is so much greater than the force it needs to come, the force you supplied is so much less than the force for them to come together. Okay? If you can supply exactly this, if same force, then they can come together. But you can't imagine the power of all these bonds. That is where when we create bombs with atom bomb, when we say we are actually breaking some of the bonds, and it's a huge amount of energy. Okay? So to form things together, you need so much energy, and whatever you are supplying is not matching it. Now, in covalent bonding, so ionic bonds, that's all we are going to look into, not more details. All you have to remember is ionic bond exists in ionic compounds created by oppositely charged ions attracting each other. There is complete transfer of electrons. Okay, that's all you are remembering about ionic compounds. Now covalent bonding, we are going to go into more detail because we have to do the Lewis structures, and all Lewis compounds, we are showing all covalent bonds in there, different types of covalent bonds. So when two nonmetals form a bond, the bond is covalent, we know that, and they are both close to the noble gas electronic configuration, so sharing will allow both to obtain it. That is why they share electrons. When two nonmetals, let's say for example oxygen and chlorine, oxygen needs only 2 more, chlorine needs only 1 more, and both are really electronegative, so they are not going to lose any of their electrons. So they are going to say, why don't we reach a mutual agreement? We will keep some electrons in the middle and share, and we both can have 8 around us, which is the same number of electrons as a noble gas. The octet rule comes from actually the noble gas electronic configuration. All the noble gas except helium, helium has only 2 around it, and that is why hydrogen, the regular element just before helium, needs only 2. Hydrogen wants to be like its nearby noble gas, which is helium. Helium has only 2 electrons, right? That is why when we learned about electronic configurations in Lewis structures, hydrogen is happy when it has 2 electrons, because when it gets 2 electrons, it is like helium. It doesn't need any more. It's not greedy. Whereas other elements, neon onwards, all the noble gases have 8 electrons around them. So others, when they form Lewis structures, they want 8 around it, which is called the octet rule. Yes, Thomas?
What about elements like lithium and barium? Are they close?
No. For lithium, when it forms an ion, it is closer, but we are talking about Lewis dot structures, where sharing of electrons. Lithium, do they share electron? Lithium is a metal, so it loses an electron. It's not going to share. We are focusing only on non-metals which are sharing electrons. So the Lewis dot symbols, which you all know, but we are going to do it one more time. So Lewis dot symbol, otherwise electron dot symbols, we place electrons as dots, right? Now dots are placed around an element's symbol representing valence electrons and pair of electrons. Remember all those things you did in lab? Okay, so those electrons are kept always as pairs, and the octet rule, which is the tendency of an element to have 8 electrons around it, which is the same electronic configuration as a noble gas, and those 8 electrons exist as 4 pairs, either as dots only or shared pairs. It doesn't matter, they just need to have 8. And ions, once again, ions achieve those 8 electrons by either losing or gaining electrons, the metals. And we are not going to talk about the metals when we do Lewis structures, because Lewis structures are for covalent compounds where they share the electrons. So just as in ionic bond, covalent bonds are also formed that each atom can have 8 electrons around them. Because noble gases have 8 electrons, an octet. Here is a 2 picture, hydrogen fluoride, which we have seen before. If you do the Lewis structure, well, one difference in Lewis structures you will see in your book and the lab is that in the book they are not using lines at all. Okay, they are going to use this overlapping pairs as lines. This could be confusing, so I absolutely do not mind if you still keep your line pattern. That is much more easier to follow than putting all the dots in and visualizing which one is bonding, which one is non-bonding pairs. Okay, so we will still keep our line pattern. Otherwise you have to put the electrons, then do the circles and show the overlapping one, and you have to think of them as the lines. So the octet rule, one more time, the tendency of an atom to achieve 8 electrons, same as the electronic configuration of the noble gas, and again hydrogen needs only 2 electrons. Remember we said hydrogen 2 is the happy state, right? So only 2 electrons because helium has only 2 electrons. That's why hydrogen needs only 2 electrons. Now this explains why the halogens exist always as diatomic molecules. We learned long ago that halogens along with oxygen, nitrogen and hydrogen, 7 molecules naturally exist as diatomic molecules, right? This explains it. If you look at halogens, each halogen, they have 7 valence electrons, right? They need 8 around it. So what do? 2 of them will come together and they will keep 6 electrons to each themselves, but they share the 7th electrons with each other. That's what is going on. So these 6, what you see outside, that is with this fluorine. These 6, that is with this fluorine. But their 7th electron, both of them will keep that in the middle and they will share it. So if you look at one of them, now they have, including the shared one, they have 8 around it. This guy also have 8 around it. So existing as diatomic molecules make them stronger because they have 8 around it now. Okay, that is why all the halogens will exist as diatomic molecules. Now what happens in oxygen and nitrogen? We know that oxygen and nitrogen also exist as diatomic molecules. Each oxygen has 6 electrons around it, 6 valence electrons, right? So when 2 oxygens comes together to make 8 around it, they need to share 2 pairs. How do we represent these 2 pairs? Remember the double bond? That's what this 2 pairs is. See, it's so easy to keep the line concept rather than putting the dots, because from this it is difficult to visualize that double bond, right? So oxygen has a double bond, which is the 2 pairs of electrons. So when you did your Lewis structures, you had the oxygens, the double bond like this, and then both of them have pairs. Similarly, nitrogen, there are 3 pairs, right? So that is a triple bond. So that is how they share electrons and makes bonds double or triple in order to have 8 around them. So steps for writing Lewis structures. It's a revision. Anybody forgot the lab or anyone quiet did not get it? This is your second chance. So the first step is sum of valence electrons. How do we calculate the valence electrons? Their group number, right? Each element, its group number represents the number of valence electrons. What do we do with ions? That is, if you have a positive or negative charge, what do you do? Positive charge means what would you do? Subtract 1, because positive charge means less electron, right? So for each positive charge, subtract 1. Each negative charge you will add 1. So that is the first step. Sum the valence electrons of all atoms in the molecule. Second step is, what did we do in the second step? Doing the skeleton, right? Decides which one is the central atom and then put others around it. How do we decide which one is the central atom? The more electronegative goes, no, the less electronegative in the center. Okay? The least electronegative in the center, more electronegative is outside atom. There were some additional rules or exceptions we learned in the lab. Let's remember them also. Carbon, if carbon present, it's always be the central atom. What is another exception? Hydrogen. Can hydrogen be a central atom? It can never be a central atom. Yes, remember them. Then what do we do after we get the skeleton? We connect the central atom with the peripheral atoms, right? With a bond. So in this step, you are going to draw the bond. That's what they say, place 2 electrons a single bond. Draw the single bond as lines, because that is much more clearer than this method, what the book shows. Okay? Otherwise you have all these dots around it and you will really get confused. So place the lines when you do a single bond, double bond and triple bond. Okay, after we connect everything, what do we do with the rest of the electrons? Starting with the peripheral atoms, start giving everyone 8, right? Start giving everyone 8, and then last step, check whether everyone has 8. If not, make the adjustments, right? Remember making the unshared electrons to bring it into the middle and making them share. So these are the same steps, guys, written probably using couple of different words, same concept. We will practice some. Write the Lewis formula for the formaldehyde molecule. The formula is CH2O. Okay, the first step is calculating the valence electrons. Carbon, how many? Carbon is in which group? 4. Hydrogen, group 1 but 2 hydrogens, so there are 2 electrons. Hydrogen is in group 1, right?
Right.
So there are 2 of them. So you have 2 electrons from that H2. 1 oxygen. How many? 6. So what is the total number? 12 electrons. Right? Okay, now we are ready to do the skeleton. Who goes in the center? Carbon goes in the center, and we are going to place the other elements around it, and we connected the outer elements with the central atom. How many electrons so far we have used? 6 electrons. How many more we have to use? 6 more. Okay. Can I have any more electrons on hydrogen? No, because hydrogen already has 2 and happy. So oxygen needs how many more? 6 more. So the first step is you are going to put those remaining 6 electrons around oxygen. Well, oxygen is happy. Who is not happy? Carbon. What do? We will ask oxygen to share a pair between carbon and oxygen. So let's say we are going to move this pair between these 2. So our final structure will be carbon with a double bond between oxygen. The hydrogens are on each side. And now how many electrons are there on oxygen?
4.
I mean lone pairs. Only 2 pairs, or because we have moved this one, right? This one pair we asked that to be shared between. So we have to erase that. So we have only, everyone is happy? Carbon has 8 around it. Oxygen has 8 around it. Hydrogens have 2 around it. Are we using all 12 electrons? Yes, we are. So that is the correct structure of formaldehyde. See, didn't I tell you when this comes in class, this becomes easy for you when we did the lab? Alright, hydrogen cyanide, HCN. Number of valence electrons, hydrogen, 1. Carbon,
4.
nitrogen.
5.
So the total is 9. Guys, total is 5 plus 4 plus 1, right? 10 electrons. Okay, who goes in the middle? Carbon. So we have a nitrogen and a hydrogen. Hydrogen is all set. So how many we are showing right now? 4. How many more we have? 6 more. Starting with the peripheral atom, you are putting those 6 electrons. Nitrogen is happy, but carbon is not. What are we going to do? We are going to make them share the number of electrons, right? So let's move one pair. We get HC double bond nitrogen, and now nitrogen has only 2 pairs left. Is carbon happy? Not yet. What do we need to do? We need to ask them to share one more pair. So let's ask them to share this pair also. So you have hydrogen, carbon. Now there is a triple bond between carbon and nitrogen has only 1 pair left. Everyone happy? Hydrogen 2 around it, carbon 4 around it, nitrogen 8 around it, and we are using all 10 electrons, right? Okay, yes.
I'm sorry, but I forgot how to tell which one to do.
If carbon is present, carbon is the central atom. Otherwise, you will check the electronegativity, and the least electronegative element goes to the center. Hydrogen can never be the central atom. So here one is hydrogen, it can never be the central atom. One is carbon, which is always the central atom. So there is nothing else to worry then, right? Let's practice some more. Draw the Lewis structures for each of the following based on the number of bonds that each tends to form. Remember to include the non-bonding electrons so that all have octet except hydrogen. So, when we have two carbons, what did we do? Do you remember? We place both as the central atom, right? We just connect two carbons and then we will do the structure. Okay, before that, valence number of electrons. C2H6. How many? So 2 carbons means 8 plus 6 hydrogens means 6. So 14 electrons. Let's calculate the valence electrons for all of them. C2 means 8. H4 means 4. So 12. C2 again 8 plus H2 2 means 10. Okay, now let's do the structures. So C2H6, C, both C's in the middle. I have 6 hydrogens. What do? Give each carbon equal share, which is 3. So we will put 3 around each carbon. How many electrons are we using? 2, 4, 6, 8, 10, 12, 14. We are using all 14, right? Is everyone happy? Hydrogens needs only 2. It's good. Carbon needs 8. Each carbon has 8 around it. So that is our structure. That is the structure of the first one. Now let's do the second one, which is C2H4. So once again 2 C's in the middle, 4 hydrogens. So we are going to give 2 on each carbon, right? Okay. How many are we using so far? 2, 4, 6, 8, 10. We are using 10. We have 2 more electrons, and who is not happy here? Both carbons are not happy. So what do you do with those 2? You have to give them both, right? So you will show that as the double bond. Now all 12 are used. Everyone is happy. The third one, once again 2 carbons, that means 2 carbons and 2 hydrogens only, so each hydrogen on each carbon. How many are we using? 2, 4, 6. How many we have? 4 more. So can we put anything on hydrogen? No. So carbons need, each carbon need how many more? Yes, I mean if you think this carbon has only 4 around it, it needs 4 more, right? Can you give all 4 electrons to this one carbon? No, then this guy will become unhappy, correct? I mean he is unhappy right now, he doesn't have 8. So the only way is making the 4 electrons be shared between these two. How do we show that? 4 electron sharing. We need to add 2 more lines. So total, there is a triple bond right there. So that is the structure. We are using 1, 2, 3, 4, 5, 5 times 2, 10 electrons. Everyone happy. Remember this? Okay. So yeah, there is this picture, but remember the structure looks much more confusing, right? Because they do not use lines for the bond. So each of these pairs here represent lines. Here look at this. This was the double bond, and this is the triple bond. So you keep drawing with the lines, okay? Because that is much more clear than putting all the electrons as dots and try to visualize which one is single bond, double bond, and which one is lone pairs. Because there is absolutely no difference. Everything looks like dots. Let's do one more activity. Draw the Lewis structures for each of the following. NF3, how many valence electrons? 5 plus 3 fluorines, so 7 times 3, 21, so total is 26. How about water? 2 plus 6, so 8. How about NO2 minus? 5 plus 12. What do we do with the negative charge? For every negative charge, we will add 1. Remember, negative charge come from electrons. We are counting the electrons. So, for every negative charge, you will add 1. Okay, so how many total? 18. Alright, now let's do the structures. NF3, who goes in the middle? From nitrogen and fluorine, if you look at the electronegativity, nitrogen has less electronegativity. Remember, fluorine is the most electronegative. So, fluorine is never going to be the central atom. So, nitrogen in the middle and 3 fluorines around it. How many electrons are we showing so far? 6. We need to show 20 more. We start with the peripheral atoms, and each of those fluorine needs how many more? Fluorine needs 6 more electrons, right? Remember the octet rule. So, you give 3 pairs to each fluorine. Are we using all 26 so far? No, there are 2 left. And who is not happy here? So you can give those 2 to nitrogen, and you are using all 26, and everyone is happy with the octet. Okay, let's do water. Who goes in the middle? Oxygen, because hydrogen can never be the central atom. So again we will put 2 hydrogens on each side. We are using 4 electrons so far. We have 4 more. What do we do with that? Put them on oxygen, because oxygen is the only one who can take them, right? Hydrogen cannot take any more, and oxygen needs 4 more. So we are good. Alright, NO2 minus. Who goes in the middle? Nitrogen. 3 oxygens. Oh, I'm sorry. Yeah, oops. Ooh. One mistake leads to another. Okay. Only 2 oxygens. Come on. Okay. So far we are showing only 4 electrons. We are going to make the oxygens happy first. So 6 to this one, 6 to this one. How many more? 6 plus 6, 12, 14, 16. We have 2 more. Where would you put that now? On the nitrogen. 2 more. We are showing all electrons, all 18, but is that picture good? What is the problem? Nitrogen doesn't have 8. So what do? You will ask one of the oxygens to share a pair of electrons. Do you have a preference? Any, as I said, both oxygens are the same. So it doesn't matter which oxygen you pick. Okay? So one of the oxygens is going to share a pair. So what will be our final structure? Oxygen, double bond, nitrogen, single bond, oxygen. Nitrogen had a pair. This oxygen has 6 around it. This oxygen has only 4 now. There is your picture. And this double bond, it could be either between this oxygen and nitrogen, or it could be this oxygen and nitrogen. And that time, this one will have 6, this one will have 4 around it. Okay? It absolutely doesn't matter which oxygen you choose. Both oxygens are equally important. Need any more practice on Lewis structures? I think everyone can do this, right? Okay. Do I need to start the next topic? Let me see. Resonance. Well, maybe this is a continuation, so we'll just do this also. So, we just see in the previous molecule also, I said the double bond could be between either of the oxygens, right? Here is another example, SO2 molecule. If you do the SO2 molecule also, you will get like this, sulfur with oxygens here. I'm just going to show you only the bond. There are two possibilities, okay? Either the double bond between this oxygen and sulfur, or the double bond between this oxygen and sulfur, just like the NO2 minus molecule. When we have like this more than one Lewis structures, remember in the lab also you had couple of other examples where you had more than one Lewis structures, right? Like NO3 minus was another example. So when we have structures like this, we will call this phenomenon resonance. Okay? Resonance can be think of like this. Let's say we have the photograph, the back side and front side of a shell. When you look at those two photographs together, in your mind, you can have a three-dimensional complete picture of that shell, right? If you see only one side, you know, your imagination is not complete. But when you see both sides, now close your eyes and think about that shell. Do you see the complete shell? Right? That is how our mind works. You can kind of connect that to the resonance. In the molecule, when you see those two different structures, the actual molecule is a blend of these two. It's not actually either this or that. It's going to be a blend of these two structures you have drawn. And this phenomenon is called resonance. So, well, let's do this activity also. We have another good 5 minutes. So, if you do the structures of N2O, well, it has shown that the atom arrangement is N, N and O. So, what are the possibilities? How many valence electrons we have here? 5 times 2, 10 plus 6, 16 electrons, right? So, we are showing 4 now. Come on. So 1, 2, 3, 4, 5, 6. 6 plus 2, 8 plus 2, 10. We can show 6 more. So normally we will start with the outer one. So I put all 6 in here.
Why is the N in the middle?
Because oxygen is more electronegative than nitrogen, so it cannot be in the middle. So one nitrogen has to go in the middle. If you check the electronegativity, oxygen is 3.5 or 3.4, nitrogen is only 3. So that is why it specifically say that also the atom arrangement is NNO. It cannot be in the middle. Oxygen cannot be in the middle. Okay, what is wrong? What can we do? We have to make this nitrogen happy. The options are, you can make this sharing here and one sharing from here, right? So that will give you the structure like this, N double bond N double bond O, and then this oxygen with 2 lone pairs. This nitrogen is also with 2 lone pairs. Well, another possibility is that instead of asking the oxygen to share, I will leave the oxygen alone. I will ask this nitrogen to share one more pair. Or in other words, your structure will become nitrogen, triple bond nitrogen, single bond oxygen. This oxygen still has 6 around it, but now this guy has only 2 around it. This is also a possible arrangement, right? You are still using 16, everyone is happy. So these 2 possible structures, these are called the resonance structures. And how do we represent resonance? These are the two structures we just wrote. One is double bond between nitrogen and oxygens, and here triple bond between the nitrogen, oxygen doesn't, yes.
There, that last structure they have there, oxygen doesn't have 8 electrons around.
Yeah, that is actually stupid. That is why this dot thing can be so confusing, because when you put dots, this can happen to you also. You know, when you count, it becomes like, ooh, yeah, you need, I think, 2 more here, right? Anyway, so the two structures, when we have loose structures, what do we do is, we draw both structures and we put a double-headed arrow between them. So when you see two structures with double-headed arrows like that, that means both are same molecule, different loose structures.
Are we going to have to write both?
I will have a question like that. Yes, we will do more practice on this in the next class. Possible loose structures, and there will be a question like that. Draw all the possible structures.
For every question that has a resonance.
Every molecule do not have resonance. Only very few molecules have resonance.
I mean in the test, if there's
So in the test, yes, as I said, I will give at least one molecule with resonance, and I will ask you to draw the possible structures.
Can you go a couple slides back to show how, I don't know what happens on
Do you just want me to go back? Yeah, right here. These are the two resonance structures. So I would put a double-headed arrow between them just to show that that's your resonance structures.
And it's carbon that's always in the middle.
Carbon is always in the middle. If carbon is not present, the least electronegative atom is in the middle. Okay? Alright, let's stop right here. Next class we will finish this chapter.